Definitely not an easy problem. We'll start out putting in the radius for each of these. So we're going to draw this in. Of course, that's 1 inch, half of the 2-inch diameter. And then if we complete this triangle here as a right triangle, we know that that aspect ratio is the reciprocal of this one, because the radius has to be perpendicular to that line at the point of tangency there. So we're looking at this aspect ratio, 1 to 2. We invert the 2 to 1. And I added the hypotenuse to that triangle so we could work with it. So the length of this hypotenuse across here is going to be square root of 1 squared plus 2 squared, 2.236 inches. So we can use that to find, I'm going to call them dimensions A and B here, on that little triangle we drew. So we're going to have 2.236 relates to 1, in the same way that 2 relates to B, or 2 relates to A, sorry, those are both horizontal. So we'll cross multiply and divide. 1 times 2 divided by 2.236. Gives us 0.8945. So this is 0.8945 here. For B, similar proportion. 2.236 relates to, what did I do here? Relates to the 1, yep, is the same way as 1 here. This 1 relates to B. So 1 times 1 divided by 2.236, cross multiplying and dividing, gives us 0.4472. So that's B here, 0.4472. Now I don't have room to write it in. We're just going to keep it here. So right now we have 2 of the 3 pieces we need for this. We have B, which goes from here to here. And we have the radius, which goes the rest of the way up, just going to be 1 inch. We need to find the distance from here down to the bottom of that groove, or whatever you want to call it. To find that dimension, I'm going to look at this shape here, which is just this shape taking out of there. The distance across here is going to be 2 times the 0.8945. Giving us 1.789 inches. Now this across here is 0.500 inches. So the dimension on each side here has to be half of the difference. So we subtract the 0.5, we have the 1.289, and we're going to divide that by 2. This is 0.6445 on each side. Really, all we need that for is to find the height. The height, of course, is just going to be this dimension here. And that does go off of that 2 to 1 slope. So if I call that dimension D here, 2 relates to D in the same way that 1 relates to 0.6445. Cross multiply and divide, that'll be 1.289. So this is 1.289. So we have 1.289 here, 0.4472 472 here, and 1 inch exactly here. If we add those three together, oh, what do we get? 2, 16, 13, 7 and 2. So 2.7362 inches is that total height. That's from the bottom all the way up to the top of the ball. And we know from this dimension here that from the bottom just up to the top of that point is 2 inches. So x is the difference. We subtract those two measurements. You get that x is 0.7362 inches. If you found that, just give me a wave. Does anybody have questions on how we got there? That's a very common tactic or practice, is to divide it up into pieces like that and add them up to get a total height and then subtract from another known benchmark. So that's not an easy problem, so please don't get too discouraged about it. There is a quiz out there that is due tomorrow by the end of class. That quiz is on all those tapers and stuff that we looked at yesterday in class. The one problem that we did in class is on there. For that one, you don't have to do a whole lot other than just make sure you put down the answer that we came up with. Today we want to keep working on, we're working on that same packet with the tapers in it. And we're going to work on some of the other topics that are in there. Today and tomorrow we'll do that, finishing up Unit 1 tomorrow. And what I'll do is, for those of you that would prefer a hard copy of the test will be Thursday. I will give you the hard copy of the test to take with you at the end of class tomorrow, so you have it. And then Thursday's class will be a test day. For those of you that come into campus for Thursday, as long as you work on the tests and get it done, I'll have you turn the test in on Monday. So I will be logged into the class on Thursday, but for those of you that would prefer, you can just use it as an extra hour in the morning. You don't have to get to campus quite so early. So anyway, some other applications of these ratios and proportions that we're looking at. One is something called a mechanical advantage. Now, mechanical advantage comes into our simple machines. And what it is it is a ratio of output force to input force. For example, if you have a pulley system, you have this pulley set up like this, and you have whatever it is you're trying to lift hung on that bottom pulley. Let's say that this weight that we're trying to lift is 100 pounds. When you pull on the rope, you're only going to have to pull with about 50 pounds of force. Slightly more than that because there's going to be a little bit of friction in the pulleys, depending on how easily the pulleys turn. So this is the 50 pounds here would be the input force. That's sometimes called the effort force. That's how much effort you have to put into the system to get it to move. So that would be 50 pounds. The 100 pounds, then, that's the object we're trying to lift. That's our output force. Now, of course, the pounds cancel out. Just like any other ratio, it has the same unit, so the units cancel out. 150 both can be divided by 50 to give us that this is a 2-to-1 ratio. So that would be a 2-to-1 mechanical advantage, is what that's saying. So whatever it is you're trying to lift, you need to put in half of that amount of force in order to lift it. Well, that might seem a little too good to be true. What is the trade-off? The trade-off is distance. They just called that the effort distance. I should call it input distance here. The mechanical advantage, output force to input force, is the same ratio as the ratio of distances. Notice, though, that it's input distance over output distance. This is an inverse relationship. So if I need to lift this object here a distance of 20 inches, we're going to have to pull on the rope here twice as far, 40 inches. How does that trade-off work? Well, a simple machine conserves work. Work is a force applied times the distance traveled. So over here, input work and output work have to equal the same. Well, the input work was a force of 50 pounds times the distance of 40 inches. Right up here. The output work was 100 pounds times the distance of 20 inches. Notice either case, 50 times 40 or 100 times 20 is 2,000. Pounds times inches is inch pounds. So this relationship does conserve work. The amount of work put in is equal to the amount of work that comes out. We just use that distance, that change of distance, to alter the amount of force required. Now, there are other types of simple machines that we work with. A very common one is a lever. Well, let's say we have a lever sitting here, and we're trying to move an object that is going to require 800 pounds of force to move it. Can we predict the amount of force that we're going to have to push down on this lever with? Well, we can. This is our fulcrum here. Excuse me. The distance from our fulcrum to where we're going to lift, we're going to assume it's the very end of the lever that's lifting on that. Let's say we know that that is 15 inches. If we know from that fulcrum, that pivot point to where we're going to push, we know that distance is 75 inches. Again, it is a ratio of the distances, but it's an inverse ratio. So it's the input distance over the output distance. Input distance is 75 inches, output distance is 15 inches. The inches cancel out, that's a ratio of 5 to 1. Well, we know our mechanical advantage will also be that, but the mechanical advantage, of course, is inverted. It's the output force, the input force. Again, remember, for distance, it's output on top. For force, for distance, it's input on top. For force, it's the output that goes on top. That'll equal a 5 to 1 ratio. So we're looking for 800 pounds of output force. When we cross multiply and divide here, it's going to require 160 pounds input here. So with this lever set up the way it is, 160 pounds of force put into that lever can lift that 800-pound weight. Our ratios come into play in a lot of other applications as well. One of them is alloys. If I'm going to mix an alloy with a 6 to 1 ratio of aluminum to zinc. I want to know how much of each metal is needed to mix 56 pounds of the alloy. One little trick that we can use, and it's useful in quite a few situations with our ratios, is to get a total. There's 6 parts of aluminum and 1 part of zinc. 6 plus 1 is 7 total parts. And once we get that total, we split our ratio up into a ratio of one substance out of the total and then a ratio of the other substance out of the total. So for aluminum, there is 6 parts aluminum out of 7 parts total. Because we did the 6 plus 1 to get 7. And here the 56 pounds represents the total weight of that final alloy. Now we cross multiply and divide. 6 times 56 divided by 7. That's 48 pounds of aluminum. For zinc, well, zinc is 1 part out of the 7 parts total. Again, the 56 pounds represents the total alloy, the total finished alloy. We cross multiply and divide. 1 times 56 divided by 7 gives us the alloy would take 8 pounds of zinc. So like I said, a handy little tool with our ratios is taking a ratio that compares, especially if those are the only 2 ingredients in that mixture, that if it compares the 2 ingredients to each other, change it to a ratio that compares each ingredient, or into 2 separate ratios, I should say, that compares each ingredient to the total. Now we have some ratios that might be 3-part ratios instead of 2-part ratios. We might have a ratio that is 5 parts silver to 2 parts copper to 1 part zinc. Those ratios are a little off, but that's basically the recipe for sterling silver. If I need, again, I'm going to ask how much of each. I should say that this is a ratio of by weight, not by volume. How much of each metal is needed to make 72 pounds of alloy? Well, we can do the same thing we did with the last one. We have 5 silver, 2 copper, and 1 zinc. 5 plus 2 plus 1 is 8 total parts. Now we can do each of these separately. For silver, silver is 5 out of the 8. So we get, how much is that out of 72 pounds? Cross, multiply, and divide. That's going to give us 45 pounds. We can do the copper. Copper is 2 out of the 8 parts. Find out how much that is out of 72 pounds. Cross, multiply, and divide. That's 18 pounds of copper. And then finally we have the zinc. Zinc is 1 out of the 8 parts. How much is that out of 72 pounds? 1 times 72 divided by 8 is 9 pounds of zinc. That should add up to the 72 pounds total. Another place where these ratios, well, you know what, I'm going to hold off on those till tomorrow. For right now, in the packet, we had you do up numbers to page number 72. I'm going to have you do number 72. Sorry, 73 and 74, sorry. 73, 74. And then we're going to have you do 77 through 85 for tomorrow. We've got about 17 minutes left. I'll let you have that time to work on these if you like. I'll be on the network to answer any questions as they come up. Otherwise, that